Start streaming. Streaming. Public packages from last day open. And put in charge. Co's responsible. You're in charge. Remind me just before 9 o'clock that it's just before 9 o'clock. Yeah. Excellent. Well done. Gentlemen. Yeah. Just about 9. Yeah. Sure. Maybe. If we can get through just a little bit now, then we can do that. Yes. Yeah. Okay. From the handout last day, as we were doing different types of examples, Dylan, Luca, class has started. Don't need to yet. Step out. Not talking to each other. We were doing it with different types of atoms, showing how they go through. If we were to do it with what we can actually measure in a lab, so I'm going to erase the other things I wrote last day. You can just write below. I just don't have to scroll through all of it. Let's once again reestablish. If you can do it in molecules, you can do it in moles. So if I have 1 mole of carbon, how many moles of hydrogen gas will I need? 2 moles. And how many moles of methane gas will I make? 1. Okay. So if I was to go into the lab, how do I measure out a mole of carbon? It's okay. 12 grams of work. How many grams of hydrogen gas would I measure out? What? You lost yours. There we go. Stoichiometry. Hey, let's try to find if anybody else is missing one. So we're still on the first page for those of you who joined in. I've erased some stuff that you can look over. How much does 2 moles of hydrogen gas weigh? 4 grams. Because 1 hydrogen gas is 2 grams. I've got 2 moles, so 4 grams. How much does 1 mole of methane weigh? 16 grams. Now, notice, while our moles may not add up, you don't have 1 mole plus 2 moles equals 3 because you're making a larger molecule, our mass will always add up. Law of conservation of mass, 12 grams plus 4 grams goes to 16 grams. That's always going to work. However, you're not going to go to the lab and weigh out 4 grams of hydrogen gas. If you can accomplish that, that would be fairly impressive because it's in a balloon and that balloon is going up. You'd have to have a very specialized weigh scale to measure that. How would you measure out 2 moles of hydrogen gas? Okay. Put in liters. How many liters is 1 mole? So 2 moles. 44.8. Get the man have a chance there. He's good. And then how many moles and liters would you make of the methane? Pardon? Not 44.8, 22.4. And that is something you can do. You could go and you could get 6 grams of carbon. You could get 44.8 of hydrogen. Once you run that over, the carbon will disappear and it will convert to a smaller volume of gas. There's 22.4 liters in a mole, and there's only 1 mole of that one. And these ratios now work for everything. I probably can't handle 44.8 liters. That's quite a large number of milk jugs, which are 4 liters each. But I probably could handle 4 liters. So that's probably a reaction I can do. I think I've mentioned the reaction in which I almost blew up the lab. Be very careful when you're multiplying and dividing amounts because the heat will multiply with it. This process, if it's exothermic, would come over that. You'd multiply the actual amount as you go through as well. So we can now use this to calculate useful numbers that we can actually then go into the lab and do. Setting that up, let's turn into the next page, which turns out I just printed the front page twice. I didn't actually intend that. And it just has more stuff in the bottom. I think I meant to erase the first one, but I'm going to use it regardless. The reaction we're going to do is the classic. So balance. And then because people always complain about my writing, let's paste this in here. There we go. Calculate the mass of H2O created from 14.2 moles of oxygen in an excess of hydrogen. And now this things everyone has read. That's wrong. We are block E. And where's here? There he is. Andrew? Yeah. Dylan? Yeah. Eshwan? Jillian? Jillian is going to be late. Chloe? Chloe? Yeah. Logan? Yeah. Luca? Luce? Yeah. Luke? Yeah. Milan? Yeah. Nick M? Yeah. Nick L? Ryan? Tatum? Yeah. Taylor? Excellent. So in that particular case, we can do 3 people, I think. Yeah, we do that. Okay, find your group. Except for the last 2, you 2 separate and join another group. So there's 2 groups of 4, and the rest of the group is of 3. Go to a board, right, and solve the question I just gave you. I want to see your work. Grab a whiteboard pen, pick a spot. Yeah, just go join another group. So there's 2 groups of 4. Didn't she just walk in? There we go. Okay, everybody in their groups. There you go. There's the question. I will enter that into my school. Forward, no, host, no. Schedule, there it is. Yeah, that's terrible. I'm gonna hide that. Here. And why the H2 is the other 2 being 32 makes sense. I'm not sure about the other 2. Look at that. Oxygen, hydrogen, or water? What? So you'll need, what moles do you need?
oxygen out of this whole thing. So we just take it.
Why is the molar mass of H2O3? Hasn't changed. Well, now the moles are 28.4. When the moles was 2, that oxygen grams that changed the molar mass. What's the molar mass of oxygen? You're wrong. I don't want to check the molar mass. Well, it could be one step on the path. I could use that number to get there. So I would erase the number. These people did something over there. You know, that's a wonderful grams. Grams of what?
Calculate the mass of water.
Excellent. Oh, yeah, you have another.
So it's just the equal amount of hydrogen.
Yeah, just whatever you need. It's like you're throwing a party. How many burgers can you make if you have 54 patties? You have excess of 5.
Oh,
Excess.
okay. So if we find the grams of how much is in this, how much hydrogen there is.
Then that might work. This
Yeah.
So.
Like,
Yeah. What is that number? This is. Oh, okay. 4 grams. Why is it 4 grams? Oh, okay. There's something in there that will work. It's not right there, but there's something in there that will work.
This is 32 and then 2.
You can show other people. Ooh. Works as well. Which one's ready? What numbers is that? Which one? That would be good. Your units are with stuff. Why is it presented as a form? Right? Grams times mole would be gram moles, not per. Also, what 18 is the units in 18 to 32? Right? That is your mole. Yeah, that's right. Yeah, there you go. That kind of works. anyway, 35. Okay. Have a seat. First of all, that was great. Balanced it correctly. You're approaching it from law of conservation of mass, which makes a lot of sense because that's what you're used to. I'm going to show you a really efficient way to do it, but you almost independently, in many cases, came up with another method I'm going to show you called the table method, and where you line things up. That one I think got closest to that, which will help sort all your numbers in the right spot. But overall, you're all getting there, it seems, through conservation of mass. If we were to, first of all, I should probably put down the balancing that we put. We need 2 and 2. So we know we have 14.2 moles of oxygen. So we have 14.2 moles of that. What's the ratio of water to oxygen? 2 to 4? 1 and 2. So we have 2 waters for every 1 oxygen. So we can now treat what we're talking about like we do units. We know we need double the water, our oxygens cancel, and we get 28.4 moles of H2O. After that, it's just a calculation as you would do in any of our calculations we've done before this. You've got so many moles, you multiply by the molar mass. And that gets you there very quickly. So you can now use ratios and multiply by them to turn it into a different species. So you have oxygen. I asked you for the mass of hydrogen. Instinctually, I noticed everybody just figured out the mass of oxygen because you could, and that's exactly what you should be doing. Say, for example, in your test on Thursday, you got something you want to convert to something else, but now we can move things. We can move them over. Now, once you had that, most people looked at it. Well, they didn't stop there. They figured out the mass of hydrogen as well, and they went, oh, well, those two added together has to equal that, and that's true. How we organize to show that's true, we're going to get reactions that are fairly complicated. So I'd like you to draw this table. There's a way that we set up. So I'm going to re-put the reaction here. You're going to need about 3 rows. I'm going to make it nice and big just so we have lots of room. But now, the table method is a way of just organizing your work so you can lay everything out and see where it goes. I lay out mine in a particular way. Mr. Snow lays out his in a different way, and I'll show you his method. They have advantages and disadvantages. I put moles in the top because the moles will follow the ratio. So I want them right next to each other. It also gets used to something for next year called an ICE table. I also put the units in, so I don't have to put them in every box. If you put them in the beginning, we take them as read for the rest of everything else. Here's the data we're given. We're told that, oh, this is 14.2 moles. And then you can start filling out anything else you think you might need. This is the area for the molar mass. So if you thought you needed it, you'd put 32.0 grams. Well, you wouldn't have to put the unit. We already put it in the beginning. 32.0, and you can keep going along, put anything you want in there. Many of you calculated down here that this was 454 grams. However, if we were to move from one species to the other, we have to take into account the coefficient. So over here, we multiply by 2 over 1, because it's a 2 to 1 ratio. So if I'm jumping from here to here, and multiply, pick a darker color, multiply by the coefficient I'm going to, and divide by the coefficient I'm coming from. And the key part on there, multiply by what I'm going to divided by what I'm coming from. So what that works out is if I'm going from here to here, it's in a 2 to 1 ratio. I'm going to this one and coming from that one, multiply by 2, divide by 1, and that gets us our 28.4. If I'm going from here to here, what would I multiply by? It's just 1. 2 over 2, 28.4, 1 over 1. If I'm going from here, times by 2, divide by 1. So this is how much of this we're going to use up. It said it was in an excess, which means you have more than enough. But that's how much this reaction will use up. So this will also be 28.4. Now we can solve it in any particular way that we like. We know that this is 18.0 grams per mole. And so we can solve it going down and say, oh, I've got 511 grams. If you're organizing it in your table this way and you're showing your units either in the boxes or along the side, you don't need to separately show all the calculations. Anything that's in a table and you've done it correctly, I will see that you've shown your units and shown you how you do it. What is the molar mass of this? Hands. Yeah. 2. I also heard 4. So we have to get a cage and put people in it and fight it out. Hands up if you think it's 2 grams per mole. Hands up if you think it's 4 grams per mole. That's pretty much a tie. I think we should just say it's either one and we move on from there and then you can just pick. This is a very common thing to happen as soon as you start balancing equations. When we have calculated the molar mass of H2, have we ever had to worry about the coefficient before this? We have not. We haven't changed what H2 is. H2 is still H2 gas. We just put it in an equation. If I had a different equation, C plus H2. No, I have to add oxygen. I'm not going to do that complicated of an equation. We wouldn't change the molar mass. I think what might have happened is here we had 4 grams because we had 2 moles of it. And then that became 4 grams. But to calculate that, we still used, in this particular case, that was still 2 grams per mole. That was 12 grams per mole. And this was 12, 13, 14, 16 grams per mole. It's just that we had 1 mole of this one here. We had 2 moles there, so we had to double it. But this stayed 16. We didn't do anything special with that. The coefficient doesn't double that. So it is, in fact, 2 grams per mole. Dylan, question? Does it seem disturbing? Yeah. Well, how else can I put it? You haven't changed the identity of what hydrogen gas is. It hasn't become H4. And so its identity. Oh, you're yeah. It's just 2 separate ones. You just need 2 of them. If you have so many moles of it, it's still 2 grams per mole to figure out how much that weighs. This is the coefficients are just showing how they react. For someone who got this number down here, what was the number of grams of hydrogen? 56 something or what? 56.8. So you could use a table to figure out the mass, add them up, get that. You could use this to go straight to the number of moles there, use the molar mass, get it that way. There's usually a couple of ways that you can get at a particular angle. We'll add concentration down here at some point, and add some rows to this table. But this will fundamentally be the main ones you'll probably end up using most of the time. We don't calculate everything off of here. I don't tend to put molar volume of a gas on there, for example. I say take the moles out, do that as a separate calculation. Because otherwise students start to confuse it with the volume for concentration. But you can if you want to. It's just a way of organizing your work. Okay, 847. We got to the point where I kind of wanted to do in terms of introducing stoichiometry. If you would like to start studying now for your test on Thursday, you no longer have to remind me when it's 9 o'clock because I wanted to stop by then at least. Reminder, I'll be asking for your Hebdens in, taking a look for that on test day. We probably don't need